Okay.
Hello, everyone. Welcome to our weekly Brazilian Algebraic Geometry seminar. It is a great pleasure for me to introduce today's speaker, Hossein Movasati from Impa. He will speak on Ibiporanga, a modularized space for differential equations of automorphic forms. Please, Hossein.
Okay, thank you, Caroline, for giving this opportunity to talk in Brazilian Algebraic Geometry seminar. So today I'm going to talk about a kind of moduli space that it's almost more than 12, 15 years that I'm trying to handle this kind of moduli space. And since at some point I realized that there is no, it's a kind of new, so I got the courage to start putting the name Ibiporanga, but it's not officialized, but anyway. So I will talk about moduli spaces. And I have to say that really there will be not time to talk about differential equation part and also automorphic form. At the end, I will tell how to get automorphic forms from this purely algebraic picture. But mainly, I will be focused on the moduli space itself and why one has to construct it, and actually one has to construct it as explicit as possible. Okay, so. Okay, so maybe I start with some citation from Andrew Wave, which he said that there should be a book on an article about the history of moduli spaces and so on. And maybe the important aspect of this quote is that we have to go to elliptic functions, elliptic integrals, and nowadays the language more period. And okay, and so let's go further. Okay, so I'm going to talk about a book that I have written. The book itself is a kind of project. It's a kind of project that it took some 300 pages to write it. So this means that if you want to fulfill all the details of this project, it takes more pages and so on. So I will be mainly in the first two box of the project. So after defining algebraic drum, cohomology, Gauss-Manning, we will not. I will not talk about Gauss-Manning connection, but Hajj filtration, polarization, etc. To introduce this moduli space that I will call it T. Well, this is the Portuguese word that I use, Ibiporanga. But anyway. And so the book is maybe it is going to be published this year, and I have to say that really I have to say there are parts of the book which I would say that one has to make it more rigorous. And one example you will see soon. Okay. Okay, so let's go to. So first of all, why do we have to generalize? So my idea is just I want to generalize automorphic forms. I don't care too much about application for now, and why this generalization? I mean, but one has to be justify this generalization, and maybe I have to say just a few examples. For example, if you go and look for the story of the solution of the Fermat loss theorem by Andrew Wiles, then you will see that at the end of the day, there will be some elliptic curves. It becomes a statement of elliptic curves, and then it becomes a statement about a modular form. And in this context, the modular form are holomorphic functions in the upper half plane. So these are let's say imaginary tau bigger than 0. And all these justification that I want to mention, I don't have a really profound understanding of these applications. But at the end of the day, I know that the modular forms are there, they have been useful, and so on. Maybe another very useful application has been in let's say something called Monstrous, Moonshine, Conjecture. So this is about a modular function J, which is again a function in the upper half plane. But at the end, it has to do with the monster groups, the representation of monster groups, and the dimensions of all these, the representation. At the end, it turns out that something called the modular function G is responsible for is the generating function of all these dimensions and so on. Anyway, this is again some application that really I don't have I'm not expert at it, but anyway, this is there. For more than let's say 150 years, the J function was in the literature of mathematics, but after almost 150 years, there was Conway, Borchardt came, and a lot of other people stating and proving this conjecture. Anyway, what I want to say, it is reasonable to just to generalize modular form for the sake of generalization, and that's the thing that I am going to do. Okay, so let me start from a consequence of Hereshmann's vibration theorem, and if in the whole talk I will mainly consider a subfield of complex number. When I'm in the topological context, I will consider the field of complex number itself. But let's say, for simplicity, if you want, you can take the base field, the complex number. So I will have a family of smooth projective varieties. And from this one, I will just, subvariety of Pn times T. T is some another variety. In most of the cases, is smooth. And P will be the projection on T. And if I use differential geometric language, then this pi will not have critical points and values. In particular, all these fibers, xt, p minus 1t, they will be smooth. So one consequence of Hereshmann's vibration theorem would be that all these projective varieties, x, let's say t1, they are the same in the C-infinity category. And so this means that in the C-infinity category, you don't. They are the same. They are the same manifold. Of course, in the complex and algebraic context, the fibers are different. And of course, if you're more arithmetic, the behavior must be from fiber to fiber is different. And okay, so let me. So one consequence of this theorem is that, so as I said, the fibers are all the same in the C-infinity category. This means that there is a C-infinity map. So the one consequence of this statement would be that if you take the cohomology rings of xt1 with z coefficient, this at the end will be, I will use it. This is a ring with the cup product, and there is also let's say polarization. So this polarization will be elements in H2 the realm of xt let's say 1. So let's call the index 1 here. So this will be the same as if you just change the from x to t2. Z, the cup product, and theta 2. What this means that at the end of the day, there is an isomorphism between these two guys, preserving the indices. I mean the grading, this grading here, and it will preserve the cup product, and it will take the theta 1 to theta 2, the polarization to the polarization, because they are in the same projective space. So this is the topological picture. Actually, for this one, you have to just consider our C. And at the end of my talk, this guy will appear again. So let's go to more algebraic context. I think I will close the windows. So from 90 to 1950, the people started to develop cohomology theory, check cohomology, and check cohomology, singular cohomology, and so on. But inspired by Andre prediction of the existence of algebraic cohomologies in algebraic geometry, Grothendieck made, let's say, a breakthrough, let's say, kind of definition that it doesn't matter. So if you take just K, any field of characteristic, 0. Maybe I start writing better. That's just a moment. Okay, so for this one, K will be can be a field of characteristic 0. But for my purpose, as I said, I will put our subfield of complex numbers. So so we have this our projective variety, let's say Pn. Maybe if you want to take this one of this fiber that I had in the previous slide, and if you want to, you say that it is defined over this K. So the breakthrough is that one can define these cohomology rings, these guys, which are K vector space. So these are actually K vector space. And once you assume that, let's say you embed your K inside complex number, you tensor it with C, they will be C vector space. They're actually the classical de Rham cohomologies. So in order to distinguish between these two de Rham cohomology, I will put X infinity here. This means that I am considering X as a C infinity manifold. So the breakthrough that it is possible to define these objects, and moreover, we can define a lot of other things together. This one, let me see. Okay, another things that we can define it is the polarization. Let's say, okay, and maybe the Hajj filtration. So this guy, maybe if let me fix here some M. Okay, so there will be a filtration here, F0, F1, F2, and so on. This filtration actually in the complex context, when we are working over complex numbers, originally it comes from Hodge decomposition, but Hodge decomposition is defined through harmonic forms and so on. So it's not algebraic way of defining an object. But maybe the observation do the telling that we can define this Hodge filtration. And in the language of the Hodge decomposition, it is just, for example, F. Let me say, let me clean again. So. Okay, so HM the RAM X. When we are in the we consider it as a complex manifold. This has this decomposition. Hn minus 1, 1, blah blah blah. This goes on, and then the Hajj filtration is just making these pieces together. So Fm is just this one. Fm minus 1 is these two pieces, and then three pieces putting together, and so on. So despite the fact that these single pieces are defined by harmonic forms, and you cannot define them purely in algebraic geometric framework. When I'm saying algebraic geometry, this means that you just define it by polynomials and not else. And whereas these pieces are defined by harmonic form, they are solutions of certain differential equation, they are infinity object, and so on. Anyway, we can define also this Hajj filtration. These are K vector they are K vector space. And what else we can define? And of course, one observation also, we can define the polarization. This is theta H to the RAM X. Again, this our K. And well, in the languages of the Chern classes, this is the Chern classes of the O1, this which comes from your ambient space, Pn, and then you will get an element here. And one ingredient also the same. Maybe I have to mention also this one. Okay, so this cup product also you can define it in a purely algebraic context. So remember that when we do course in algebraic topology, we define cup product, I mean, with using infinity things. So Hn, the RAM, X over K, then going to Hn plus Mx K, and that then alpha beta goes to alpha cup beta. So if you are in the infinity context, this is just this is alpha classical wedge product of the infinity differential form. So, but when you go to singular cohomology, then instead of you don't have differential form, you will use cup. In the algebraic framework, we will use this notation of cup for this. So anyway, so far what is the observation? So you can define all these objects. Currently, I don't have any watch. I don't have any idea of the time. Maybe you get 5 minutes before you tell me. Yeah. Okay.
Okay, I tell you when you have 5 minutes left. You have just started, so you.
Okay. So we have this cohomology ring. We have cup product. We have this Hajj filtration, and then we have this polarization. And since let's okay, so this one you can define our arbitrary field. Okay, so remember that by Ehrenmann's vibration theorem, since these guys, so maybe I write here, since these guys Hm, the RAM X infinity, and at the end of our complex number, this is the same. This is by Ehrenmann's vibration theorem. If you took this one, they will be the same. The RAM X2 infinity. They are the vector space of the same dimension. But now I will reach to the very fundamental proposition. Okay, a proposition which seemed to me trivial, and this is the whatever I said at the beginning. I wrote a 300-page books, but I think there are a lot of places in the book that one must make them rigorous. In particular, this proposition, the proof at the beginning that I gave to this proposition, it was some involved with some intuition and so on. But let me first explain the proposition. So take the same family that we started at the beginning, and I will fix one fiber. So this is very essential until the end. One special fiber will be always fixed. And something also maybe for the purpose of completeness, I have to say, usually one has to take families of varieties which are complete in the sense that you cannot deform its fibers outside your family. For example, you have to take family of non-isotrivial family of elliptic curve. You have to take a family of Abelian varieties which contains all possible deformation of Abelian varieties and so on. So, but anyway, in an example, we will see. So you cannot just take one parameter family and start developing theory of just with one parameter families. The family must be kind of full. Okay. So you take these two fibers, two regular well, all the fibers were regular at the end. So the point is that there is this 2x structure that you build for x and x0. They are the same. And there is no difference between two structures, even so that x and x0 algebraically, analytically, they are different varieties. We know that their topology is the same. So they are topology infinity in the category of infinity manifold. They are the same. So this will at most will imply that these two guys, together with this cup product, and if you are a little bit work a little bit together with the polarization, they are the same. But the point is that Hodge filtration, there is no version of Hodge filtration in the singular cohomology. So the proposition that even the Hodge filtrations of these things are the same. So you cannot. The exact statement will be this one, that there is an isomorphism between these two guys, respecting the grading. So M will go to the M. So this isomorphism will take polarization to polarization, will respect the cup product. And of course, it will take the pieces of Hodge filtration isomorphically to pieces of the Hodge filtration without changing the indexes. So this means that Fi will go again to Fi in the other cohomology. And despite the fact that you have defined these things over arbitrary field, anyway, the conclusion is that it's a kind of topological invariant of your variety because it doesn't distinguish algebraic or analytical structure. Okay, so for the first time I gave proof of this one, I mean, it was based on intuition and so on. And at some point, there was some conversation, email exchange with Denin. And well, he arranged for some rigorous proof, but I have to say that this proof uses SGA3 going to chapter 9, and then and really it is beyond my mathematical knowledge to go to all this EGA and FGA and to say that okay, I know the exact proof precisely. But anyway, and the funny part of the story is that even so that the theory that I'm going to tell you is based on this proposition. In examples, in many examples and many articles that I wrote, I could check this one by hand. So, so this means that you can develop the theory even even if you don't have a rigorous proof for this. Anyway, so I will. Well, let's proceed further. So the start, now let's start from, let's say, our object of the moduli space that we are dealing with. So the object, well, I chose the word itaquachiara, written, painted, or stone. So this is simply the projective variety together with this what isomorphism. What is this isomorphism? As I said, I will fix a fiber x0, and this is just alpha is just a comparison of this guy together with the structure that it had with the x0 one, x0, and then its Hajj filtration, cup product, and so on. And it seems very just one enhancement of the variety, but actually it is when one works with concrete examples, it is more than it is a have to say it's a collection of data. Why I would say, in practice, one has to take maybe okay. Let me see if I can use erase it. Okay. So in practice, one has to take a basis of this drum cohomology, let's say. So the whole drum cohomology, one has to take a basis, let's say mi. This means that alpha m being in hm and then I indexing the basis in hm. And then one has to use alpha to transport them here. So this data of alpha in the way that I presented a single object, but actually when you do this choice of basis, it is it's a frame of the cohomology ring of your variety X. So okay, so in the next rest of my talk, what I'm going to do, the enhancement that I want to do it is with this alpha, and well, as I said. Even in the case of elliptic curves, really to say that this enhancement existed in the literature, well, I have to say it's a very I didn't I never found, and then I have to generalize further and further. But let's go further. So and then once I have inserted my moduli space, so this will be the collection of all these x alphas. And then modulo, let's say, some natural equivalence relation. And of course, if you can define what is this natural equivalent relation. So this relation, you just have h star x1. Then you have the comparison of, so well, I will not write cup product, Hajj filtration, and so on. So you have this comparison of these things. So there is a cup product and so on here. Then with x0, and then it's a structure, and then this is alpha 1, and then you have h star x2. Its comparison with this guy. So this two, let's say, x1 and alpha 1 will be the same as x2 alpha 2. If x1 and x2 as algebraic projective algebraic variety are same, this means that there will be isomorphism between x1 and x2. This isomorphism will induce isomorphism here. This will respect the Hajj filtration, cup product, and so on. So the idea is that this, let's say this alpha 2, so the equivalence relation would be that this must commute. Anyway, this is a kind of natural way to say that when two objects in my moduli space are the same. So this is the point-wise description of the moduli space that I want to deal with. And well, anyway, once you have a moduli space in algebraic geometry, it's not just set of points. You would like to put a structure, analytic space, or algebraic variety, scheme, stack, and so on. So let's Well, I will be scared to put the kind of conjecture on this one. So let's call it a kind of wishful thinking that this moduli space has a structure of a quasi-affine variety. This is a very important aspect. These moduli space are supposed to be affine, quasi-affine variety. This means that they are supposed to have a lot of functions, a lot of regular functions on them. And that they must be over some reasonable field, but I think maybe you have to put also Q bar here. It doesn't matter. And a very important aspect also that in many examples, there is a universal family over this moduli space. If you are expert at least in one example of a moduli space in algebraic geometry, you know that there are coarse moduli space, fine moduli space. In many situations, coarse moduli space exists, but fine moduli space doesn't exist. This means that there is no universal family on such. But since because of this addition to my projective variety, this makes this our moduli space more tame in the sense that you don't need really to go very strange spaces to talk about languages of stacks and so on. Anyway, in the rest of my talk, I will give examples of this, and you will see that how the things happen. Maybe let's go to the case of elliptic curves, and this is.
Hossein, can I ask a question?
Exactly.
So do you want your moduli space to have morphism to MG or something like that? In the case of the X is a curve.
No, exactly. In this moduli space, at the end, there is an algebraic group that I will not talk about. When you make the quotient with this algebraic group, this acts on my moduli space, and at the end, this quotient will be the classical moduli space. This algebraic group will eliminate this alpha in some way.
So if that's the case, it's you cannot hope for quasi-affine, right? Because the moduli space of curves is not quasi-affine.
Yeah, of course, but the point that there is algebraic after taking a fine quotient of a fine variety by some algebraic group, of course I can get many wild moduli spaces. They are not quasi-affine. Maybe even they are not quasi-projective. So this is the point. Before this bigger one might be quasi-affine. Maybe in the case of elliptic curve, this is also clear. This bigger moduli space, maybe it behaves well, but the classical moduli space, which is that taking a quotient with some algebraic group, will be as complicated as you know.
Okay.
Okay, so maybe okay. So let me. Okay, so let's say the case of elliptic curves, and actually started to develop this kind of moduli space in 2008. And well, I started from some project of Griffiths that at the end of this project of Griffiths it stopped where it started. And so the idea was that he wanted some automorphic form theory for Hodge structure and so on. And then I had to reformulate this one. And of course, in the area of elliptic curves, we have a lot of repetition. And of course, I repeated a lot of works of masters like Klein, Fricke. I was reading 3 volumes of Fricke. There are a lot of huge computations about elliptic integrals, elliptic curves, and so on, that at the end, they are there. And if one reads them, one might get into this moduli space. Of course, in the time of Fricke, there was no concept of moduli space in the way that we are taking now. But anyway, the case of elliptic curve, I have to say that there are a lot of people involved. But if you want to really look at as a moduli space, modular problem, then I have to write it. And in this case, so you see that this moduli space will be this affine variety. So it is a 3-dimensional object. And as I said, that there is a universal family here. So if you have a T1, T2, T3, a point, just let's say a geometric point in this moduli space, you will have this family of elliptic curves over that point. And so the kind of novelty was this T1 that you see a lot of computation in the literature related, but you don't find really this T1 as a true parameter of the elliptic curve, because at the end you can translate X and eliminate T1. But okay, remember that our moduli space contains a basis of the de Rham cohomology. So I have to specify what is the base of de Rham cohomology. And it turns out that if I want to use the language of old language of differential forms that the people use, like Weierreich and so on, this will be the differential form. So just don't be scared that these are not meromorphic differential form in y equals to 0. If you restrict these guys to the elliptic curve, this meromorphicity will disappear. And so at the end of the day, this moduli space in the case of elliptic curves, one can write down it explicitly. And this is one moral of the story, is that I don't want just the existence of the moduli space. For example, all this category theory stuff and so on in algebraic geometry, most of the time they guarantee for me that, okay, such moduli spaces exist, and maybe if I'm very lucky, maybe the universal family will exist also. But for practical reason, I have to construct my moduli space as explicit as this one as possible. Maybe I say a few comments about George's what George said. So here, if you take this from a map from this one to let's say P to C, and this is the map is just given taking the point T1, T2, T2. It's going to take it to G invariant of the elliptic curve. It will be, if I remember, 27 T2 to the 3 minus, or T3 to the 2 minus T2 to the 3, something like this, and then T2 to the 3 is up. So this will be a map from T to A. And let's say this algebraic geometric notation, and this is three-dimensional. This is the one-dimensional. This will be the classical moduli space of elliptic curve. There is no universal family like this one over this A1, but and actually the algebraic group that in this case I was telling is just there is this k minus 1, 0, k prime. Oh, these are elements. Let's say all these things are in k prime in SL. Oh, sorry, it's a complex number. And okay, the action of this one also, it is very explicit. I didn't prepare this one, but once again, the moduli space that we have it might be nice, but once you make this action, it might be you get some quasi-projective or some and even it might be that moduli space that you cannot construct it in the framework of schemes or so. Okay, but let me go in this talk. I will just mention the examples. Okay. So maybe the case of principally polarized Abelian varieties is also nice. And here I put 3 points before Thiago's work, because of course his work on the construction of the moduli space is based on the classical, the construction of the moduli space of principally polarized Abelian varieties itself, which is and few other results. And but if you take this results that the moduli space of the principally polarized Abelian varieties behave well and so on, then you can prove this. You can check this wishful thinking and make it a theorem. And maybe I have to say a few further things regarding this case. That actually the works in Ziegel modular forms might even lead to this one. Maybe I mentioned this. Okay, I have not defined what is Ziegel modular form and so on, but whatever it is, at some point, Igusa, one of the masters of Ziegel modular forms, he wanted to construct as explicit as possible the algebra of genus 2 Ziegel modular form. So he got 5 transcendental functions. It doesn't matter whatever it is. So and then he realized that there is a relation. So this T35 is just notation, and then there is square. The square of this one is a polynomial in 4 other variables. And then this is the only relation between these 5 generators of Ziegel modular form and so on. But the moral of the story is that if you take spec of this one and a spec, and then in geometric context, this means that you consider this affine variety. This affine variety is actually very closely related to a smaller moduli space in this framework. Of course, Igusa never talked about this moduli space, but what I am saying that this explicit polynomial that even Igusa computed, and he writes in an article that it took several days for him to compute this horrible polynomial. Then actually we compute a kind of smaller version of this moduli space. So this is a kind of related, and of course from this one to construct this T moduli space explicitly, this means that the set of generated. So this is the main issue. And in the Thiago's article, we don't see the affine, the algebra of regular function of this moduli space explicitly. And so there is still some work to do if we want to see explicitly, maybe. And at some point in with Yau and Jin Chao, we have to do this one. So this result I will not mention. But what I'm saying that it is possible to write down these algebras as explicitly. So if T is quasi-affine, this means that you have the global sections of the ring of regular function T, and then you wish that what is the let me say what is the minimal embedding dimension. So this means that you what is the smallest embedding of T inside some Cn if we are working on projective space and so on. And it turns out that even that this T is of a smaller dimension, for example, in this let me say in this way. For example, even so, let's look at the genus equal to 2 case. Even so, this T is of dimension 10. We know that it's affine variety, but when we want to embed it in some Cn, it turns that we will need more than something 153 regular function on it to distinguish points on T and so on. So, so what I'm saying here is theory. Then in practice also you can find some interesting problem. Okay, let me. Okay, so let me go further. Maybe I will say also the case of Calabi-Yau variety. As I said, today I will just stay in the case of the moduli space problem. So after a long series of works and so on, Vivek and Subsidus, for example, to prove that the coarse moduli space of polarized smooth Calabi-Yau three varieties exist as a quantitative projective variety. So this means that it has a nice, and as far as I remember, it might be to reframe these results over some field, but for the moment, just let's say over C. And another classical result that this above moduli space is smooth. So this smoothness, well, actually the theorem is more detailed. So that one part of the theorem is that this moduli space is smooth. Its dimension is this h n minus 1, 1. This is the Hodge number of the underlying Calabi-Yau variety. But what is the moral of the story for our moduli space? This Ibiporanga that so the corollary would be that this is in our case also it is a smooth algebraic variety. Actually, when let's say the projective, well, it doesn't guarantee that it is affine or quasi-affine, but at the end it guarantees us that it is it has the structure of a projective algebraic variety. In dimension 3 we can even compute the dimension. And then there are some partial construction of this moduli space. For example, there is a dwarf family of Calabi-Yau variety. That in this case, you don't need Vivek's results, or you don't need the Mumford geometric invariant theory. You just sit down and construct your moduli space, like in the case of elliptic curves, and there are partial results here, and this article. The moral of the story of this article that if you want to do physics, even you don't need to construct moduli space. I mean, this business of constructing moduli space is the business of mathematicians. The physicists, they don't care. And if you want to reach some new territories, maybe you just assume that it behaves well and start doing computation. And even so, here the results are on this moduli space on Calabi-Yau threefold. We just take small patches of this moduli space and do computation. And really the construction is not here. But well, just for the sake of complexity. Okay, I found my telephone, so I have the track of my time. Okay. So I mean, this one also I wanted to mention because just recently I was working with Roberto and Jin Chao. The whole the whole project can be done with mixed Hodge structure, and this means that for varieties, if you instead of X project a smooth projective variety, if you take not necessarily projective, not necessarily smooth, then you will have apart from Hajj filtration, you will have weight filtrations also, and then, I mean, it's a kind of new territory. You just start developing the theory for this one. But this kind of theories are useful in examples. So in order to just have a feeling what would be useful, then we started with this case of elliptic curve together with 2 points. So this guy, there are the notion of relative de Rham cohomology that also you can define a purely algebraic context. And so if you define a similar enhancement and so on, and it turns out that you can find out your moduli space as a affine variety, and you can start constructing the moduli space. And it's a kind of good exercise to see if it is worth to write down the general theory. So you see that the families, we have the Weierstrass family of elliptic curve. O is the point at infinity. So this is written in the affine coordinates. When you compactify it, there will be a point at infinity. Let's call it O. Then P, the second point will have coordinates A, B. They will be they will appear as independent parameters in my moduli space, because at the end we are considering moduli space of elliptic curve together with 2 points. And then you can write down the differential forms and so on. And well, this one also needs another talk. Starting from this picture, you will get a theory, the theory of index 0, 0 Jacobi forms. Jacobi forms. So the idea is that then if you do this the kind of nonsense geometric construction, you are toward the theory of the Jacobi forms. And again, I will not justify why Jacobi forms are useful. And you will not see here also in this talk. But the moral of the story that you can construct this. Okay, so this is the example that I collected. Maybe let's see. Okay, I have Carolina. É uma hora, não?
Sim, você tem mais 9 minutos.
8 minutos. Okay, come on. So I didn't tell about all these other boxes that was in the project, but at least I have to say a few words. How do you translate this algebraic framework into some transcendental functions? And these transcendental functions will at the end will be automorphic form and so on. So I will go right to the beginning of my talk when I talked about Hershman's fibration theorem. And I told that all these projective varieties are infinite are the same. So as I said, I fixed this projective variety, and there were other they were popping up in a family, T in T. Okay. So let me say, I used T twice. T at the beginning was parameter space, and then the T as the moduli space. For my example, these two became at the end the same because my moduli space there was a universal family. So I will not distinguish between these two things. Anyway, I will take this group. So this is the automorphism of this my cohomology ring, respecting the grading coproduct, taking the coproduct theta 0, taking the polarization theta 0 to itself. So they are z-linear, respecting the homology grading, they're respecting the cop, a theta 0. I have not defined a monodramic group. The monodramic group usually will be subgroups of this group. These are discrete groups. And in many interesting examples, like as Calabi-Yau varieties, even this is infinite index. This inclusion is our infinite index. So but in many interesting examples, the whole of this automorphism group can be also the monodramic group itself. So for the sake of simplicity, I will take this gamma z as my monodramic group, and so this is a discrete group, and in order to take my thing to the transcendental world, I have to define something called the Monodramic Covering. And so this is again in the same framework of the family that I was working. You don't need to go beyond this one. So it will be the enhancement of my variety together. So first of all, the polarization now has coefficient z, so everything is discrete. And I know this delta is this isomorphism. So this means that by Hershman's theorem, we know that these two guys are isomorphic. If you want, you put xt just to distinguish the total space X with the fibers. But anyway, now the enhancement is with this delta. In the case of this T moduli space, the dimension increases because my enhancement itself has moduli. But this enhancement will not increase the dimension of the moduli space of X. The reason is that these guys are discrete. This delta is discrete. So basically, this is just choosing a basis of homology with z coefficients. So they cannot move, so they will not contribute to the moduli space, to dimension of the moduli space. But of course, you can still make this enhancement. So this is a kind of, I have to say, this is a kind of H tilde is a kind of universal covering of classical moduli space, like this AG of moduli space of principally polarized Abelian varieties. But anyway, one has, instead of really universal covering, one has to take this one.
Just to tell you that you have 5 minutes, as you asked.
Okay, thanks. Okay, so, and in general, well, so this will be a kind of complex analytic variety with infinite number of components. So you have to take one component of this guy. So maybe just I tell. Oh, so the bridge between algebraic world is given by some transcendental function t that you construct from this h to this t space. And whatever regular function that you have, like a, this let's say in the case of elliptic curve, there was t1, t2, t3. When you make the pullback to here, you will get Eisenstein series E2, E4, E6, and so on. So you will get that, anyway, just a transcendental function. And since, well, in general, I don't have the recipe how to construct this T explicitly. Case by case, I had to construct this T. Maybe I have to say, let's say the case of elliptic curve. So let's just write down the elliptic curve case. So in this case, this H is actually isomorphic to upper half plane. Set theoretically, remember that it was just let's say variety enhanced with some delta and so on. But so let me say, so the point here. But the point here was E the elliptic curve, let's say, together with two differential forms in the first in H1. And actually, this map is given by, sorry, here it is a delta 1, delta 2, because they were in the homology. So it is a kind of taking a holomorphic 1,0 form over, integrate over delta 2, then integrate over delta 1, holomorphic, the same omega 1,0. And that this quotient doesn't depend on the choice of omega 1,0 because the space of holomorphic one forms of elliptic curve is one-dimensional. And then since your moduli space already comes from this delta 1, delta 2, you can do this one. Anyway, just since I have I am running out of time, maybe okay. So maybe I just say a few words about this one. So what is this map? This map is let's say okay. So this map takes tau to, of course, the elliptic curve will be this z tau in the complex framework. This tori, then what? No, I have to enhance it with two differentials for alpha 1, alpha 2. They are uniquely characterized by the fact that if you integrate alpha 1, alpha 2 over your delta 1, delta 2, that your moduli space coming. So here there are actually delta 1 and delta 2. Then you will get this type of matrix up to some to tau minus 1, let's say 1, 0. Anyway, this is again a transcendental function, and you define it, and then your algebraic geometric framework, if you consider our complex number through this transcendental map, the ring of functions will be translated to ring of regular function on some affine variety will be translated to ring of holomorphic function on certain domains, which I will call it H. Anyway, I could just to mention that at the end, it's not just, let's say, trying to construct a modular space. We want to construct these algebras and so on. And this algebra that we are getting here, they are closed under certain differential operators, and that's why there appears a differential equations of the Eisenstein series and so on. But maybe I just try to finish. Since in this digital seminar, well, online seminar, there is no coffee, I took this quote from Underwood. It's a very nice, let me read. I would go to work aided by food, blah, blah, blah. And then he's talking about a servant girl was employed to clean the department, especially to serve every professor both before and after classes as many cafezinos as he wished. And this is I found it in the memories of Underwood in 1942-3, when there was World War II in Europe. He escaped to Brazil, and then for a while he was in São Paulo. And yeah, that's it. Okay, thank you.
Thank you, Hossein. Questions or comments for Hossein?
So, Hossein, are many of the details of your talk in the book on your webpage?
Yeah, exactly. I mean, this is in my webpage. There is a list of books, and if you find this automorphic form, modular forms, and beyond, this is the, maybe I show you the title once again. Just a minute. So the name of the book is Modular Forms and Automorphic Forms and Beyond, and it is well, it is under editing, so it will be published end of this year. And one of the things that if we want to do really rigorous mathematics, one of the things that I was really trying to do it to understand this the fundamental proposition of the book, that I didn't care, really trying to see this why it is correct. And of course, one has to a little bit get master in EGA stuff. But everything is there, and of course there are examples, and examples in are spread in many articles.
Are there more questions or comments for Hossein? So just I have a naive question. So you mentioned as example the elliptic curves. You also mentioned AG and Calabi-Yau, but so these are, you were always working in the smooth case, right? Or do you allow also for singularities in your variety?
No, this is the point. As I said, if you want to allow singular varieties, you have to go to the category of mixed Hodge structures, because at the end you want to enhance your variety with the cohomology ring. But in this case, the cohomology ring, apart from Hajj filtration, there's also weight filtration. Mm-hmm. So in the category of mixed Hodge, I took the simplest one, relative cohomology with boundaries in 2 points, of course, but you can take also singular varieties. And actually, it has to do with one of the boxes in the project. You have to go to the partial compactification of this modular space, because this is also, when you are doing business on modular space, you are interested in the boundary strata. And that and then you will see that you have to develop the theory even in this direction, mixed Hodge direction. But this is really complicated. I mean, even the simplest case of a smooth, it took for me a long time to write down the details and so on. And as I said, also in many aspects, maybe some proofs are not rigorous. So even the written things must be made rigorous, I think.
Thank you, Hossein. Are there any more questions or comments?
So what would be the next step, right, on this theory?
Well, this is a very I would prove to embed this theory inside Lagrange's theorem, Lagrange's theory. But the point is that it is another huge theory. Just for the sake of that, I have generalization of the automorphic form. That doesn't mean that I can sell my product to the people in Lagrange's product. I think, if I want to really prove something concrete, some conjecture, I mean, sometimes in pure mathematics, you can sell to your product once you prove some conjecture of big guy. The side of automorphic forms seems to be a long way to go. Maybe even, I don't know, when there will be some application in this automorphic form part. But I would say that I also wrote some chapter in my book about something called Hodge loci. And there is a consequence of the Hodge conjecture, which says that the Hodge loci are algebraic varieties. So they are given by you define it as analytic varieties, but at the end the Hodge conjecture will imply that they are given by polynomials. This consequence of Hodge conjecture is proved by Delin, Catani, Coupland. I think the proof is not satisfactory, and I would say that one try to prove this consequence and prove a stronger version of this consequence. The stronger version of the consequence says that the Hodge loci is defined over Q bar. So the Catani-Delin-Coupland theorem says that it's algebraic variety over C, so it doesn't specify the field of definition, but it's a conjecture to say that the field of definition is just Q bar. It's a reasonable field. So I would say, and I wrote some chapter in my book saying that there are natural foliations in this moduli space. They are in the Hodge loci becomes leaves of these foliations and so on. I would say to try at least to prove this statement. But of course, this would be for the reason of just, okay, I want to solve some problem which is open, and in this way I sell my product. But of course, my wish is that to sell this kind of thing to people in automorphic form theory, and to say that this can be useful for this purpose. But I think until the end of my life, I will not be able to do this.
Okay, thank you.
Are there more questions? Comments for Hossein? So if not, let's thank Hossein again.
Okay, thank you for inviting me. Okay, now that's good.